I know that Xavier would be here, but I don't know.
He was here.
Yeah. Okay. I will remove my mask now. Hello. Good morning, everyone. Can you hear me well back? I don't know if the microphone is working, but I think if you hear me, it's fine. So good morning and welcome everyone to the H2020 RTR 21 conference and the session Solid State Batteries, the Chemistry of Tomorrow. My name is Martha Yalabuki, and I'm project officer at SINEA, the European Climate Infrastructure and Environment Executive Agency. Today, 3 projects will be presented in this session, Astrabat, Safely Move, and Solidify. All these projects were started almost 2 years ago at the beginning of 2020 and have been funded under the same topic, LCBAT 1 2019, with the title Strongly Improved, Highly Performant, and Safe Solid-State Batteries for Electric Vehicles. They will complete their activities in about 1.5 to 2 years. So today's presentations will highlight midterm results. So as it is well known, the European climate policy wants to have the continent, the Europe continent, climate neutral by 2050. This pushing towards rapid implementation of electrification of transport. So OEMs consider solid-state technology as a solution that could replace the current lithium-ion technology based on liquid electrolytes. The reason is the need for higher energy density, but also inherently safe batteries. So new technologies, materials, and production technologies have to be developed to strengthen the European industrial base. So the projects of the session today are developing further the current solid-state battery technology and presenting solutions for solid-state electrolytes. Their work includes, among else, cell design, interface optimization, characterization, and integration. So I think it's time to welcome our first speaker, Guinevere Giffin, who will present Astrabat project. Guinevere is working in Fraunhofer Institute for Silicate Research and Julius Maximilian University, Würzburg. So Guinevere, the stage is yours. Thank you.
Okay, thank you very much. I'm happy today to present on behalf of the whole consortium our project, Astrabat. Astrabat is the all-solid-state, I can take the mask off to present, sorry, all-solid-state reliable batteries for 2025. Our consortium is built up of 14 partners from 9 different countries, 5 RTOs, 9 different companies. The project is coordinated by CEA, and it will last planned for 42 months, so starting from January 2020 and running until the mid of 2023. We have partners along the whole value chain, from materials companies to companies dealing with implementation and all the way to the end of the value chain. The specific objectives of Astrabat are to find a better cell architecture using all solid-state electrolytes, so specifically looking at hybrid electrolytes to enable us to achieve high energy and high voltage and to make reliable and safe all solid-state cells. So specifically, we want to design the electrolytes specifically for the high-energy electrode materials. In our case, we're focusing on silicon on the anode side and on NMC, nickel-rich NMC materials on the cathode side. In all of these steps, we specifically want to look at processes that are compatible with mass production. So in order to get to these larger high-energy cells. In addition, we have some specific efforts focused on alternative and future-looking architectures to make eco-designed power and energy type cells. So these will be in the pre-prototype phase, where our main cell type will be in the prototype phase. Of course, as a solid state, safety is one of the most important aspects to be considered, specifically as a replacement for liquid cells. And so we want to specifically look at the cell architecture with respect to safety, in addition to, of course, the energy density and performance. And finally, to look at the structurization of the whole value chain. So keeping in mind aspects like the eco-design, end of life, and the recycling processes. So some first results, or midterm results. So first looking at Analyte and Catholite formulations. One of the specific things that we've done is basically say, okay, there is no one electrolyte that exists to this point that can really cover the full range. So deal with, for example, the volume expansion of silicon, and at the same time provide the high energy, the high voltage stability of the NMC materials. And so we designed two separate electrolytes for each individual compartment, so an Analyte compartment electrolyte and a Catholite compartment electrolyte that will then be put together in the final cell. So we had KPIs of 4 millisiemens per centimeter and 0 volts to 4.5 volts to cover the whole range. And basically, we have achieved both ends of this electrochemical stability range through our different electrolytes. So on the anode side, we're looking at a hybrid polymer based on ether functionality. On the cathode side, we're looking at fluoropolymers to be compatible with the NMC materials. In addition, we've looked at other components, or are looking at other components to make our hybrid electrolytes, so specifically LLZO, in order to integrate into the electrolytes themselves, and then also new lithium salts and new ionic liquids. So here on the left, you can see the LLZO that's being developed with a particle size of about 1 micron. This is particularly important when we come a little bit later to some of the new architectures for 3D printing, that it is below this 1 micron size. On the bottom right, you see a Catholite membrane that has produced very homogeneous, containing the Catholite polymer, the salt, the ionic liquid, and the LLZO. We have plasticizers in these formulations, but as you can see from the membrane that's being produced, these are true solid-state mechanical membranes. The liquid is simply there, present to help with the ion mobility, and it's non-volatile, and that's definitely important. On the anode side, we're looking at formulations with nanosilicon. So we have 6 different grades that have been optimized and investigated. And we, with the anode capacity limitation, we are getting about 1,000 to 1,500 milliampere hours per gram. We're using here, what's interesting in terms of the final upscaling and processing is we're using conventional production methods for the anode itself. So this means all of the existing production equipment can be used to produce the electrode, and then the polymer electrolyte formulation is coated on top of the anode itself. I mentioned that we were looking at additional architectures in the pre-prototype phase using alternative production methods. So here we're working on the formulation of inks for inkjet printing. Our 2 partners, IRCEA and IKTS at Fraunhofer, are looking at the formulation of the NMC ink and the LLZO ink, with the idea basically of printing different structural components to improve the performance, particularly the power performance. So you can see that from the inkjet printability test that we have developed a printable ink, and at the moment we're working on adapting or adjusting the inks to contain, for example, the fluoropolymer binder for the cathode side. Of course, everything we do in Astrobat, we want to make sure at the end will comply with all certifications and standards required by the EU. So we have Elaf and Lamartov who are working on these aspects, particularly to look at the safety requirements, look at the environmental performance, LCA, to comply with all of the new regulations in terms of safety standards and so on. Specifically, they're using a live LCA-based eco-design tool to look at the environmental performance throughout the whole project. So from the beginning, in close contact with the materials producers, all the way to the end for the final Astrobot prototype. And so basically what we want to get is a selection of the best trade-off between the sustainability parameters and the performance. In terms of the impact, specifically we're looking at a large number of new materials. So we have new anode materials, new cathode materials, and several different electrolyte components. These we're looking to combine, or are working on combining, in new cell architectures. And so it allows all of our partners to continue to contribute to the new value chain for batteries with European actors. So basically to tackle the dependence of Europe on foreign competitors. And then we want to promote the deployment of electric vehicles by developing basically a disruptive battery technology. So the materials producers you can see here with some of the examples. Specifically looking at the processes, you have IRSA, IKTS from Fraunhofer and UNESCO, and then the cell architectures from CEA, Leclanché, Elaf, and Stellantis on the bottom. Finally, as I mentioned, eco-design, safety, environmental impact of the prototype is particularly important and where we feel that we can make a lasting impact. So by including a safe by design approach, that is in compliance with all of the EU directives and certifications and standards. And finally, we're using innovation and market monitoring along with a specific IPR management strategy to ensure that our technology has a very good chance or a very high chance of staying in European manufacturing facilities over the long term. So, thank you very much for your attention.
Thank you very much, Guinevere, for this very interesting presentation. So we can move on to the second project, is Safely Move, and it will be presented by its coordinator, Maria Martinez Ibanez. Maria has been working at CESI Energy Gune since 2017, where she joined the Solide Electrolyte group. So Maria, the floor is yours.
Thank you, Marta. Okay, first of all, I would like to thank the organization for inviting us. I'm here to represent the whole consortium for Safely Move. And I'm really glad to attend an event face-to-face, finally, and meet here some of the partners that are already involved in this project. So, say that, Marta already introduced myself. I'm Maria Martinez. I'm coming from CIC Energy Gune, and I am the coordinator of Safely Move project, where Safely Move stands for Advanced Solid-State Safe Lithium Metal Technology towards Vehicle Electrification. So this project was granted under the call H2020 LCVAT 01 2019. We are 15 partners where we are covering the whole value chain. So there are partners involved on material manufacturing. There are also several research centers and universities. We have battery manufacturers, and also we have end users, such as Toyota or, for example, Renault. This project is a 48-month project, so we are more or less in the middle of the way. We started the 1st of January of 2020, and today I'm going to present the most relevant results and also, of course, first the main objective of this project. So moving to the objective of Safely Move aims to support a change towards high energy density batteries. So we are aiming to a really challenging values of 450 watt-hour per kilogram and also above 1,000 watt-hour per liter. So to reach this target, we have identified the main action points, and we have divided in 4 main points. So everything is related in this case to the material development. So first of all, we have identified that we need to develop high specific capacity lithium metal battery, the lithium metal anode, sorry, with a low thickness in order to reach this target by means of energy density. Then if we move to the positive electrode, we are developing nickel-rich layer oxide cathodes that has the intrinsic advantage of the high voltage. And in order to put everything together, we need to look into an electrolyte that will replace the flammable liquid electrolyte and at the same time allow us to work with these high voltages and also the reactive lithium metal. So for this, we are developing advanced hybrid ceramic polymer electrolyte, HCPs, that they will improve the electrochemical stability, but also we are looking for high ionic conductivity, where the target is above 10 to minus 4 Siemens per centimeter. So the intrinsic safety of this electrolyte, so we are talking about a thermal stability above 200 degrees, will allow us to reduce the external safety requirements if we consider the battery pack or the battery module. And in this way, we will also have an impact on the total cost of the battery. And then the fourth point is that since we are developing many different materials, we need to put everything together in a battery, and we need to make sure that all of them are compatible. So for this reason, there is a work package fully devoted to the evaluation of the different interfaces that we will have in safely moved batteries, and also the design of these interfaces to ensure an effective lithium transport. And for this, we are working on the chemistry modification of the different particles or materials, and also the overcoating strategy. So as it has just been presented, we are also working in safely move with a bilayer concept. So this means if we consider the requirements of a separator or an electrolyte, we need to have high ionic conductivity, stability against the anode, that in this case is lithium metal, and also good mechanical properties. And then now if we move to the cathode side, the requirements are slightly different because we need to work in high voltages, so we need to have a high anodic stability. Of course, again, enough ionic conductivity, and in this case, we need to have good binding properties. So having this in mind, we have designed a bilayer concept where we are going to work with one type of hybrid electrolyte as separator, so one type of polymer chemistry, and also inorganic material chemistry, and another type of hybrid electrolyte for being used as catholite or binder. Then, before going to a detailed explanation of the achievements that we reached during the last 2 years, just to make it easier to follow the story, here is the diagram of how Safely Move have been arranged. So we have 4 different phases that are related to the different development of different generations of materials, but also cells. So in the first phase, we have the level 1 materials that are being designed and developed to be tested in coin cell level and also in monolayer, so lab-scale cells. Then the testing of this level 1 material has provided enough feedback to develop the level 2 materials that have been upscale to be tested in the first safely moved prototype of 1 ampere-hour cell. Then the same will happen with the level 3 materials, and in this case, we will go up to the first and the only generation of 10 ampere-hour cells. And at the end, in the last phase of the project, we will have the battery module with 24 volts and 10 ampere-hour. So the first milestone of the project was reached in the month 7, and in this case, we developed the first, the level 1 materials, where we have the level 1 NMC with high nickel content, level 1 lithium metal with a low thickness of 50 microns, and the level 1 HCPE. So in this case, we combine the HCPE combines one type of inorganic material and one type of polymer materials. These materials were delivered and exchanged among the different partners in order to study all the performance at assess the interfaces. And in the milestone 2, in month 14, the Gen 0 coin and monolayer cells were assembled and were also exchanged within the partners. So here, the main aim was, as I was mentioning before, since there are many different materials that are involved in this development, we wanted to study how was the interface performance among all the different components, not only considering the interface between the electrolyte and the anode, but also the interfaces that we may have even inside this electrolyte, if we consider that we have inorganic particles and an organic polymer. The study of these materials and also the post-cycling evaluation allow us to identify the main failure mechanisms in this system, in this first generation of safely moved cells. And with this feedback provided in these concrete work packets, the information was transferred to the work package in charge of the development of the material, and following this criteria, we have developed already the second generation of materials within Safely Move. These materials have been upscaled and have been provided to the rest of the partners. And these materials include a nickel-rich NMC, so as we were using in the level 1 material, but in this case, a pre-coating strategy has been applied to these particles in order to improve the compatibility with the hybrid electrolyte. Then the lithium metal thickness has been decreased in order, as I was mentioning before, to reach the target of energy density, but also different wear coating strategies are being tested. And then finally, the chemistry of the hybrid electrolyte has been tuned thanks to the feedback that we reached from the evaluation of the interface between the inorganic and the polymer, and this has allowed us to obtain a more stable and compatible system. So finally, if we focus on the impact that we foresee from this project, we can divide this in five main pillars, where we have the energy density, the long-range driving autonomy, the safety, cost, and finally the European value chain. So if we go to the first point, the energy density, so currently lithium metal technology is limited to the use of low voltage cathodes, let's say LFP, and also to the need to work at high temperatures, around 80 to 70 degrees, mainly because of the semicrystalline properties of the polymers that are used. So Safely Move aims to address, and is already addressing this, by the development of this hybrid electrolyte that will not only provide high voltage stability, that will allow us to move from LFP and NMC, and as we can see here, this will have a direct impact on the total energy density that we may reach, but also the increase of the ionic conductivity will allow us to decrease the operational temperature of these batteries below the current temperature that we may find in the market. Then this high energy density will have a direct impact on the driving autonomy of the car, because if we translate this 450 watt-hour per kilogram into kilometers, we may have 700 kilometer range. And if we take into account the final target that we have for the project, that is 500 cycles, this will be translated in more than 300,000 kilometers. Then, considering the safety, as I mentioned before, and also Marta explained at the very beginning, we are looking to replace these flammable or risky liquid electrolytes, but solid electrolytes. So here, usually lithium-ion batteries imply the need of a thermal management system that is costly, as we know, and this is required to make sure that the battery is not going above a low temperature at 60 degrees, mainly because of safety reasons. So if we replace this electrolyte with a highly stable solid electrolyte, this will have a threefold impact. So improve the safety, improve the battery lifetime, and also will simplify the pack, implying that we will have a reduced cost. And this is linked to the fourth impact, that is the cost of the battery. So we envision to have, at the end of the project, 2024, a price of 100 euros per kilowatt hour. So this, of course, is considering the assumption, considering a high volume production. So for these calculations, we are considering the materials that we are selecting for the design of the battery, but also as I was mentioning before, the design of the battery pack. And at the end, the last impact that we expect is related to the European battery value chain. So where we consider that Safely Move is bringing together some of the main actors completing the whole value chain, as I was mentioning before, from material producers, battery manufacturers, research centers, and at the end, also the end with users. So say that, I would like to thank again everyone. Please, if you would like to know more about this project, you can visit our website, follow us on Twitter, and I invite you to subscribe to our newsletter. Thank you.
Thank you very much, Maria. It was an excellent presentation. I have forgotten to mention that a dedicated Q&A session is going to take place after the next presentation. So if you have any questions, please save them and ask them after this presentation. Moving to the next speaker. The next speaker is Martin de Bucuy, and he will present the last project for this session, Solidify. Martin is a team leader for all electrochemical storage activities in IMEC. The floor is yours, Martin. Thank you.
Thank you, Marta. So indeed, I will present the third project here today. That's the Solidify project. I'm from IMEC. That's here, 20 kilometers from here in Belgium, a research institute. We are the coordinator of this project, but of course, we're not doing all this work alone. Solidify, like all the projects presented today, focuses on a solid-state battery. It's a solid-state lithium metal battery, so we use a lithium metal anode and not a silicon graphene or graphite anode. And what is maybe special to our technology is that our solid electrolyte starts from a liquid precursor. So it's first liquid, it's processed into the battery, and then solidifies into a solid electrolyte. Of course, that's why it's called Solidify. Like the other project presented here, it's an LC-Bot 1 call. We started early in 2020, so we are over halfway now. We see in total we have 14 partners, different positions in the value chains, different structures as well. There are some research institutes, some companies, some universities as well involved. Some people are working on materials, for example, Umicore, Solvionic on the electrolytes or on the cathode material, Sidravi on the lithium anode material. There are some companies more focusing on cell technology, like Leclanché, for example. Solid is working on processing tools. Other companies on really the applications, like, for example, VDL or CRF. And then I forget to mention the research institute next to IMEC, EMPA and Fraunhofer, and universities which are TU Delft here in the Netherlands and Hasselt here in Belgium. So spread out over Europe, spread out over different type of companies and different parts in the value chain as well. Like I said, we are working on a liquid-based solid electrolyte lithium metal battery. Basically, it was a technology that we already had available at IMEC, but together with these partners, we want to bring it to a next valorization level, a next TRL level, which means that we need to develop manufacturing materials and processes. So based on what we had available, we need to make changes to the materials, to the processes, to see indeed how could it be fit in a larger scale at a higher TRL level. And of course, if we are studying upscaling, if we want to prove prototypes, it also means that we need to prove prototypes at a decent amp hour. So at the end, we want to prove in 1 hour amp pouch cell. To be precise, we have 4 demonstrator cells defined over the course of the project. Basically, 2 different generations of cell technology. First generation at 900 watt-hour per liter, second generation at 1,200 watt-hours per liter, and also 2 cell sizes, or smaller cell size, to really be able to focus on the extreme capacities of the cell in terms of watt-hour per liter and cycles and charging rates. And a larger cell really to show, look, we can make this cell technology also on decent amp hour per level, being 1 amp hour in total. As we are looking to higher TRL levels, we also wanted to make a study on what are then the actual costs, what are the possibilities at the manufacturer level. So that's why we also aimed here define and basically define a strategy for the processes, for the manufacturing, for the materials that allows to a cost target of 100 euros per kilowatt hour. That's in general the objectives of the project. Here I try to make it a bit more visual, to say so. So you see here on the left side, we start with where we were at the beginning of the project, which was at TRL 3 level with an IMEC technology. And you can see here in the middle, we present or we make this liquid to solid approach more visual. So we want to start from a standard porous cathode electrode. Then we impregnate it with the liquid precursors of our solid electrolyte. And after a solidification step, it becomes solid and we can combine it with our lithium metal anode. Just on top, a schematic picture of the solid electrolytes, what we call our nano SCE. So basically you can see a pellet after solidification. It's indeed solid, it's a pellet. And if you zoom in, it's basically a silica matrix with some electrolyte material surrounding it. To be able to do that, we needed to work on the material part, both on the composite cathode, the nano SCE, and the lithium anode, together with the different partners we are working there. I'll give a few schematics for that in the next slides. Of course, we also have to do the cell integration, validation, and then assessment of manufacturability and cost to indeed show, look, is this indeed possible to do this beyond TRL 6. So a few schematics on what we have done. It's only schematics that I'm showing here. So for the SCE, the solid electrolytes, we want to impregnate it into the cathode to really surround all the active material, have a good contact there with the cathode material. We also want to have it as a sheet, to basically have a separator sheet between cathode and the lithium metal anode. So here we are comparing different recipes for the precursor solution, starting from the first recipes available at IMIC at the beginning of the project, together with the partners, mainly Solvionic in this case, using their know-how on solid electrolytes as well. And on polymers as well. We defined different recipes. We selected, or we made different separator sheets, and we selected one of these to be basically put now at this period into the cell. So basically one of these has been selected and is going to the cell level at this moment, in this period. Similar approach for the cathode. Also there we have now selected one cathode that we are going to put into our cell. Basically here we start from an uncoated cathode material. In this phase of the project it was NMC 622. Later phase of the project it will be NMC 811. But now NMC 622, non-coated, and then coatings were applied by different companies. So basically Umicore took their standard coating. Delft EMP is a company that can put additional coatings on top of it by an ALD process. Different coatings were applied, and the goal of the coatings are then to have a good interface between this active material and our solid electrolyte material. So these different coatings were made, were put into cathode sheets. Cathode sheets were impregnated with the selected recipe for the solid electrolyte, the liquid precursors, and then solidified. And then again, we have different cathode materials, impregnated cathode materials, and one of these has now been selected to put into a cell. And last but not least, similar approach also for the lithium metal. It's not a question of just putting lithium metal in contact with solid electrolytes. Lithium is very reactive and will react with basically everything. So also there you need coatings, a bit similar to the cathode. But here other partners worked on the coating for the lithium anode. Basically it was EMPA from Swiss and IMIC that worked on different what we call artificial interface layers with the goal indeed to have a good interface, a stable interface between the lithium metal anode and the SCE, the solid electrolyte. Again, 3 types have been evaluated. One of them have been selected and is going to be put in a cell now at the very moment. I only show here very schematic of the cell integration. So basically you are putting everything together in pouch cells with the goal to make these first demonstrator cells that we have promised and that we have engaged to within this project. That brings me to the expected impact of the project. So at first there's a clear technological impact, I think. We really want to increase the energy density, the capacity, and the safety of the cells. I think what we promise here, what we engage to reach in terms of demonstrator cells, in terms of watt-hour per liter, is far beyond what is at this moment the state of the art for liquid electrolyte cells. So we really want to take their next step to a next level of technology, breaking to this border of 800 watt-hours per liter, which is now more or less state of the art. Of course, it brings with it an environmental impact as well. We say that we also want to take a look to the cost. If you upscale this technology, we aim at this €100 per watt-hour. So that should also allow to have an affordable, clean mobile solutions for the market, which has an impact for the customers here as well. And as a side effect of that, that has, of course, the final goal to decarbonize the transport, as you are all, of course, very well aware. Then that we think it's only possible by indeed having this technological impact and also paying attention to cost. And the last one is the economical impact. I think we also are all aware that we want to have more battery industry here in Europe as well. So I think that's indeed not mentioned at this moment here. But we really want to make this technology, where we do believe that it can has a major impact and a major difference to what is today's state of the art. We want to bring it to the next level, really a valorization level, and we want to input this into a valorization track, so it could indeed help to have here a strong local European industry of batteries. And we hope that this technology that we are putting up here can be part of that. So it leaves me only to thank you, to listen to me, and also to thank all the partners that have been involved in this project. More information can be found on our website.
Thank you very much, Martin. It was really nice. The presentation, it was enlightened. So I will give the floor to my co-moderator, Silvia Bodoardo. So she will take care of the Q&A session.
Okay, thank you very much for the introduction. First of all, I want to thank all the speakers for very nice and clear presentations. It's several years that we are speaking about solid-state batteries. So finally, some steps are taking forward. So fully new ideas are here presented, and so we hope really to see further results in future. So we saw results by the materials point of view, for example, with the hybrid ceramic polymers and the introduction of silicon-based anodes. We saw results on the cell architectures, so with the safe by design approach for the production, and also results on the production of solid-state batteries with new technologies as the liquid-to-solid approach. So, besides these very interesting results, I'm sure that some question and curiosity are still remaining, and they will find answer during this Q&A session and also during the project long, of course. So this question may be dealing with cycle life specific and volumetric energy densities, temperature range, and so on. So the session is open for questions, so please don't be shy and ask if you have any question. Okay, that's one there, please. Maybe. Joseph.
Thank you so much.
Maybe you just say
it works,
you are,
yeah.
Joseph.
I'm Joseph from Aviators Austria. Thank you very much for this really promising presentation about the solid state, because there are a lot of other opinions sometimes in the room, but thank you so much. I have one question. Have you planned also, you have now prototypes in this direction, have you planned also to develop this further in the process for not directly mass production, but small scale production in this direction? And if so, what is your plan in this direction? That would be my question. Thank you.
Okay, do you want to, maybe we start from Astrabat and just very brief answers, so that's are involving all the three projects.
So we also, as all of the projects here, we have a prototype of about 10 amp hours at the end of the project. We have the cell producers, so we have Le Clanché specifically in our consortium to assess the steps needed to go to the next production scale, and that would be, of course, one of the impacts beyond the end of the project.
Okay, so in our case will be the same in Safely Move. So we have foreseen two different types of prototypes. One for 1 ampere hour cells, that this is the one that we are currently developing, and another one of 10 ampere hour cells. So for this we have two partners in charge of this. One is Cidetec and the other one in the Basque Country also, and the other one is SAFT. So they will be the one in charge of this final prototype manufacturing. And of course, for that, from the very beginning, we are working on the design of how are the requirements for the scaling up production of these components and also the batteries.
Yeah, from Solidify, I think it's quite comment to what has been said for the other two projects. There is a dedicated task on really looking, okay, we have this technology, we have these processes and these materials, but actually how would it look into a larger line? That's basically a work package on its own within the project to really focus on these things. We involve there the material manufacturer, but also tool manufacturers to take a look to indeed how could this be. And at the result of the end of the project, we want to have this indeed a study showing, look, this is a strategy, manufacturable strategy that is indeed obtainable as it will be presented by tool manufacturers in cooperation with these cell manufacturers, which are in the project.
There's a question here in the first line.
Hi, thank you very much for the description of these projects. Indeed, I'm more focused in the module and pack design, but I'm very interested in all the developments at cell level. And my first question is for everyone, is regarding safety. Do you have any recommendation or request to the module and pack designers in order to be complementary with the approach you have from the cell level? And the second question would be for the Solidify project. Regarding the liquid to solid approach, is there any specific step in the production of those electrodes that is different from the traditional one, or is there any key step that it is out of the traditional techniques that are used in the electrode manufacturing? Thanks.
The second part of your question on the production process, the manufacturing process, and which steps might be different from a common production process for liquid electrolytes. It is the goal from our approach to indeed be as close as possible to the traditional production process, because it's less difficult than to implement in pilot lines and production lines. I think the change in tools can be more limited then. So from the cathode part of point, we don't see a very big difference. We want to keep that the same. From the electrolyte part, there at first instance is the same, to impregnate the cathode with an electrolyte. And for liquid electrolytes, it's just liquid. In our case, it's a liquid that solidifies in something solid. The separator sheet we would like to be able to handle in the same way as a standard separator, that you can include it in the cell in the same way. That asks some stringent reasons or stringent numbers for the mechanical properties of the separator. So that's something that might need dedicated tools there at the moment to work with this separator sheet. And of course, lithium metal anode, at this moment, that's not something that is really standard in standard liquid electrolyte batteries. So there, indeed, it's part of the task in the project to look indeed how can we handle lithium metal anodes. Are there special needs towards tools, environments to tackle that? So basically, it's mainly on the lithium anode, and as I see it on the electrolyte sheets, where I'm not sure that we will be able to follow the same approaches as with a standard separator.
Mr. Please, Michael, I don't know.
Thank you. Michael is okay. So
Okay.
I'm Michael Lippert. So I'm speaking for the Batteries European Partnership Association. So from the battery side. Thank you very much for your presentations. My question quickly to all of you would be: could you briefly state what level of maturity you expect your project to be at the end of the project? Martin, you mentioned it, but for all of you, and how long would you expect this to come to full maturity? But more importantly, in order to ensure that this goes a step further so that there is an uptake and industrialization, what, in your opinion, do we need to do collectively, or what should we not do in order to avoid this? So what is the important things to do to take it one step further? Thank you.
Want to start in answering? Okay, thank you. Please, Maria. No, it's
okay. I think it's working. So the maturity, I guess that, for example, by means of the prototype level that we will reach at the end of the project. So as I mentioned, we aim to reach these 10 ampere-hour cells. But of course, there is a lot to do towards this end, mainly because we are working currently in new chemistries, new materials, and we need to foresee also how will be the scalability of these materials. That this is the first attempt that we are working currently with this small prototype of 1 ampere-hour cells. And also in our case, we aim to reach also the battery module design, as I was mentioning also during my presentation. But for this, we know that we need to move fast, and it's going to be difficult to reach all these prototypes and also the battery module working. But the maturity level of this, we aim to reach at TRL level 6 at the end of the project. Since we are working with, as I was mentioning, 2 partners that they have a great expertise on the processing and also working on this solid-state technology, we aim that, and we hope that this will be feasible at the end of the project in 2024. And of course, we are looking for new possibilities on further continue the development of this project. And for this also, we have a work package that will be devoted to the design of a roadmap towards 2030, containing this chemistry and the technology that we are currently developing, and also to try to bring down also the cost of the materials, because now since we are developing new chemistries, the impact on the cost of the battery is high. So for this, of course, there is a specific work package that is working on this direction.
So we are also looking to be at about TRL 6 at the end of the project with the 10 ampere-hour cell. I would say one of the things that we have to really keep in mind is the production processes. That when we're looking at these new battery chemistries, we have to keep in mind how can it be really done on the large scale. So of course we can do all sorts of fancy things on the lab scale to come up with cells, lots of tricks and things like that, really to say, okay, here's a really good performing cell that I can hold in my hand. But at the end of the day, we need something that we can scale up. And so that's one of the keys that we're focused on, especially within Astrobot, to keep in mind these production processes and also test these types. So let's say models of these production processes on the lab scale in order to see if that can be then really scaled up. And so the key thing of what we should do is always be keeping these production processes in mind. So what we do within the project can be then very easily at the end of the project transferred to the larger scale.
It's quite similar, so we aim at TL6, like I mentioned before. It's indeed a focus in the project So we aim at TL6, and like mentioned before, it's really a task within the project to look indeed to manufacturable processes. We are making changes to our chemistry, to our processes, to indeed show what could be a process in a manufacturable environment. We are stepping away from the lab scale processes where it's very manual, very small quantities. We are taking the changes to indeed show that is a possibility. That's how it would look, and that will be input for the study as it will be presented at the end of the project on, look, this could be a manufacturable line, this could how it could be manufacturable in an industrial environment, that could be the related costs, that are the needs that are still remaining.
Thank you. There was a question behind. Michele?
Yep.
Another Michele.
Good morning, Michele De Gennaro, IT. Thanks to the panel for the excellent presentation. My question is for all of you. I understand that Gen 4 and solid state is very much at the beginning, and now the priority is to deliver working prototypes, stable prototypes, and deliver the energy density performance. Can you please elaborate a little bit further what we can expect in terms of cyclability, first and second life of solid state, and also in terms of capacity fades mechanism compared to Gen 3A, Gen 3B liquid electrolyte? Thank you.
Okay, just start.
Okay, thank you for the question. So, of course, we are in the middle point of this project, so we cannot say yet, at least from Safely Move, but I will say that it's the same in the rest of the projects on how these prototypes will work by means of energy density and the cyclability. What we foreseen is that this will be conditioned by the cycling conditions, of course, so it will depend on the rate, on the temperature. Currently, in our case, we are working I didn't include this information, but currently we are working in the rates of 60 to 40 degrees. But we aim to reach the 25 degrees battery operation at the end of the project. And by means of the cyclability, we aim for 500 cycles. But of course, we have the challenge of working with a highly reactive nickel-rich NMC and also a highly reactive lithium metal. But we assume that at the end of the project, working in a range of 40 to 25 degrees, we will be able to keep this cyclability, of course, with enough capacity retention, about 80%.
I think maybe I will move on to the second part of that question, because I think the goals for all of us are basically the same. Our Astrobot is a little different in that, unlike the other two projects, we're looking at silicon anodes. So of course, dealing with the challenges associated with silicon is and has been one of the main focuses, of course, parallel to the cathode side. One of the things that we see at the moment is that polymer electrolytes seem to have an advantage, at least for a pure silicon anode, in order to combat some of the degradation mechanisms, particularly associated with the loss of contact, the pulverization, SEI formation, and things like that. And so this is one of the aspects that we're particularly focusing on, in addition to the cathode side aspects that are basically the same for all three projects.
I think I cannot add too much to what has already been said by my colleagues. Numbers are similar, and for sure, cycling is indeed it's an important parameter to be tested and evaluated.
Thank you. Good morning. Maurizio Maggiore, European Commission. A few, let's say, specific questions and then general ones. One about performance. I think only one project mentioned the sea level, and it's 3C. What about the other ones? And the other issue, I think I will tag with what had been asked, is what is your feeling in a comparison with the state of the art? I mean, Prologium and Toyota having quite announced quite short timelines. Where do you think they are looking at what they are published and what you know about it, and where you think you are in relation with them? And then a kind of provocation question. I mean, everybody wants to keep the manufacturing project process. Maybe, I mean, for the Chinese or the Japanese, that's important because they have a huge investment. But is there any reason why there could be a better performance or other features if we don't keep the process? Since we don't have it anyway, we don't have mass production. So it's just a provocation. I don't know whether...
Maybe I will jump on to the last one in terms of the manufacturing process. We have looked at several different manufacturing processes, particularly in terms of the way of getting the electrolyte into the composite cathode. And basically, the earlier results that we can present are showing that actually keeping the manufacturing process seems to be advantageous. So basically using a concept where you make a cathode, of course, there have to be adjustments for specific solid state chemistries. So I'm not saying necessarily keeping the exact composition of the cathode. So I can't imagine that you're going to take a lithium-ion liquid cathode and simply put an electrolyte into it. But the processes themselves are the same. And then adding a couple additional steps where basically you coat electrolytes on top. And the results that we have so far show that this actually seems to work better than saying, okay, let's make everything in one big step, do a complete slurry, and make that kind of coating.
Okay, so maybe I can continue with the second question that you were asking, if I'm not wrong. So where are located these projects compared to the state of the art? So I think that the main ambition of this call was to reach these high values of energy density, both gravimetric and volumetric density. And I think that this will be one of the main differences compared to what is defined in the state of the art if we consider solid state, because of course we want to balance both these high values for energy density, what will be translated on the autonomy, of course, of the electric vehicle, but at the same time moving far from these liquid electrolytes that offer these safety concerns and flammability issues. So I think that merging both ambitions together is the difference that we are bringing with these three projects. I think that more or less, since we have more the same objectives and the same targets, we can say that this is our main difference.
Maybe Martin, you want to answer to the provocation on the production?
Yeah, so the provocation is the fact that, repeat the question?
Exactly.
Thank you.
You all said that we are trying to keep the manufacturing process. I just wondered if there was too much of a constraint and there could be advantages to be gained in not doing it. She's already said, no, we think it's a good thing. I don't know, in your case, it's the same thing. Or?
Yeah, I agree, it's the same thing. I think if it's possible to, it's not a limitation. We don't see it as a limitation in our process to see, we are trying to keep the manufacturing process as much as possible. We rather see it as an advantage. We have a technology that works, and if we can implement it with little changes to the manufacturing environment, we see it as an advantage and an added value.
And about the C rates?
Yeah, so I think we mentioned 3C for our final device. I think that's quite ambitious. I think that's quite above state of the art as well. For sure, if you combine it with this 1,000 watt-hour per liter. The purpose of that is also in the philosophy of the call. We want to make a real step forward with respect to state of the art in mainly liquid electrolyte batteries. If we can indeed combine these high capacities, this high C rate, and this decent cycling, which is asked, then indeed we have a clear advantage, and it will indeed enable a very big market on the mobility part. Because indeed that will allow to go, like already mentioned, travel further, charge faster, which is often mentioned as one of the issues with electrical cars, and keep the battery, reuse the battery for a lot of times.
Actually, I would like to make one sort of, back to the manufacturing. I tend to only think of the bulk system and keeping the old one because that's this part that we specifically work on at my institute. However, I would like to point out our project is also looking at completely new manufacturing. So looking at producing, at least in the early pre-prototype phase, cells by 3D printing. And this is one production process that I've heard, at least in several different projects in the European landscape, that is being addressed and could possibly provide a completely new manufacturing route that isn't necessarily standard, for example, in Asia.
My name is Adlen Ben Kenida from IFP Énergie Nouvelle. Thank you for the presentations, very clear and very interesting. My question concerns the environmental impact. We saw some things, especially in the first presentation, regarding the compromise to deal with recyclability and so on. But do we have a clear idea, or is there any action inside these projects to assess the impact on environment regarding or compared to existing battery technologies? Thank you.
One aspect that we tackle within Solidify is that we aim at a water-based process for the cathode. So that's not always so straightforward, for sure not with quite active materials like NMC. But that's what we were studying in, replacing the more typical, I think, NMP-based process, solvent-based process, which has a clear environmental impact, replacing by a water-based process, which should allow a lower impact on the environment.
In the case of Safely Move, we have two specific tasks, one related to the recycling assessment of the materials that we are developing within the project, and of course the batteries by themselves, and another activity related to the LCA, where we are going to compare the lithium-ion technology with the solid-state technology. So what we can find in a general way in the market, compared to what we are developing, and I think that this is something that we need to consider when we are moving to this new technology. Related to the processes, currently we are working on wet processing, let's say, so there is a need of using solvents, but we are also doing some activities related to the screening of the dry processing that we consider that will be the next step in order to reduce the footprint.
In terms of the LCA within the Astrobat project, we do also at the end of the project have a complete LCA plan. This is just starting now to look at the full prototype. However, we've also had an additional activity that's basically started quite early in close collaboration between the company doing the LCA and the materials producers to basically keep these environmental aspects present in the minds of the material producers at a very early age. So for example, comparing different potential candidate materials in terms of their environmental impact and so on, comparing potential processes at a very early age in terms of the impact. And so we have this information available to us as materials producers very early in the project. And so if we have two materials that are quite close in performance, we have the ability to already take environmental aspects into consideration in the choice that we move on within the project.
So Martin Petit from AFPN. I have a question. In two of your projects, at least, you are using two electrolytes for both negative and positive electrodes. And so it's interesting in terms of stability for the electrodes because you have different stabilities for both types. However, it comes at a cost. You have a new interface to put in your battery. What is the impact in terms of resistivity, stability? And have you benchmarked it compared to the one electrolyte options also in order to choose this path for your project?
So yeah, that is true. Of course, if any time for a solid state cell that you introduce a new interface, you potentially have a new resistance. But this is one of the aspects that we're specifically looking at. So we're looking at studies not only of, for example, materials properties of the individual materials, but of stacks of the materials. So we don't just say, here's the conductivity of this material and optimize that. We also look, what is the conductivity of the stack? In our particular case, we're using small amounts, so less, somewhere between 10, 20 or so % of ionic liquids to help with the lithium transport, and this helps to minimize the interface. To do a true benchmark in a cell with a single electrolyte, of course, would be difficult because the two materials we have are optimized for two anodes, or for two materials, for an anode and a cathode. And we've chosen them that way to basically get the most out of the materials. And so if we did an all catholite cell or an all analyte cell, we would be introducing massive problems in terms of stabilities because we specifically optimized in this direction.
So in the case of Safely Move, we'll be quite aligned to what you have just explained. I mean, we are selecting the materials according to the requirements that we need for being using high voltage cathode or in contact with the lithium metal. Of course, we could have this reference cell where we use the same material in both sides, but we know that we are going to have compromise. For example, if we take the material that we are using in the electrolyte and put it in the cathode, we know from the chemistry that we have selected that we will have compromised the anodic stability. So we expect and we assume that the performance will be worse. So for that reason, we have carefully selected different chemistries in order to the requirements that we need to fulfill at the end in the battery.
Thank you very much. My name is Analyte from Virtual Vehicle in Graz in Austria. I'm coming more from the vehicle safety and battery safety side, so I would like to ask, can you elaborate a little bit on solid-state batteries in respect to thermal runaway, thermal stability, thermal management? You mentioned it a little bit, But yeah, I would like to know, did we solve this problem of burning vehicles, or do we need to invest more into this field? Thanks.
Okay, so currently in the project we are working on the analysis of the thermal stability, but with the perspective of the material. So we have not tested yet how will be this when we are going to prototypes. Of course, if we consider the materials and we compare the solid electrolyte with a liquid electrolyte, we don't have the volatility or flammability issues that we may find with a conventional organic solvent-based liquid electrolyte. So this might be solved with the solid electrolyte. But then if we consider the battery, of course, we will need to have the effect of the different components, which we have also the lithium metal. So we know that the melting temperature of lithium metal is 180 degrees. So we will need also to consider and evaluate how will be the thermal runaway and the stability of the battery by itself, not only at material level.
I think this is an aspect that is probably planned in all three projects. So this is something by the end of the project, when we have our larger scale prototypes, we want to do these specific abuse testing to really understand what we're looking in terms of solid state. I think it's the general consensus that it should be better. But I think there hasn't been a lot of information that's really been put out yet because we don't have these larger scale prototypes to do that. On the very small scale, I think there's been a few results that have shown that it seems to delay, certainly delay significantly, such thermal events, but if it can do that on the prototype level, we have to see when we have them.
Yeah, so on material level, indeed, it looks promising, at least in our case, and I can imagine you're doing similar tests in your project as well. But yeah, how do you say it in English? The proof of the pudding is the eating. That will be the cell in the end, indeed.
There's room for one additional question, please.
Hello, thank you for your presentation. I'm Christophe Aucher from Letat. I would like to know your point of view regarding other processing, like dry processing or extrusion, regarding what you are doing today.
Okay, so as I was mentioning, in Safely Move project, we have some exploratory activity because this technology is not mature enough for being the one selected for the final process of these batteries. But this is something that we have started. So for this, we need to consider from the very beginning, once we make the selection of the materials, we need to consider if this dry processing, let's say, for example, extrusion, it will be the processing that is selected, because according to these requirements, we need to think on which materials can afford this processing. And of course, I think that in order to avoid the byproducts and of course reduce the use of toxic solvents, extrusion or dry processing will be the best choice, not only for the electrolyte, also same could be applied for the electrodes.
Is there any very short question, please, here in front? So forgive me. You already raised your hand before.
Thank you. Well, hi, my name is Jordi. I'm calling from IREC. Thank you very much for the presentations and for answering the questions. Very general question. All of you have presented NMC and nickel-rich materials for your cathodes. So how do you see that upscaling that material, even though it has really severe instabilities in ambient conditions? Thank you.
At the moment, at least for the processes we're looking at in Astrabat, as long as we're dealing with polymer electrolytes and lithium salts and things like that, we're going to be looking at probably doing a significant part of the manufacturing processes in a dry environment, because of course to dry out a polymer electrolyte after the fact is probably going to be difficult, or even a hybrid electrolyte after the fact. And so these types of issues sort of have to be solved anyway, not only because of the NMC, but also because of the other material combinations.
Yes, I think that in a similar way, same can be applied also to Safely Move. So it's not only NMC, there might be all the other components, but we know that NMC 811 is quite tricky to be handled, mainly because what you were mentioning about the stability. We also hope that there is with the overcoating strategy that we are looking for in the material development work package, this stability issue can be solved, not only for the reactivity with the ambient air for the processing, also to the chemical reactivity with the other components within the cathode.
Yeah, same for our case. I think I showed indeed a schematic on how also we coat the NMC material. At the moment it's NMC 622, will be NMC 811 in the second phase of the project. So also there, the goal is to increase the stability of the material, both during the processing of the slurry, during the processing of the liquid precursor of the salt electrolyte, and during operation that indeed the interface between salt electrolyte and NMC is controlled and better maintained than just as is.
Thank you. So I want just to close this session thanking again the speakers for their very clear and presentation, and all the attendees for the question and answering, so that we go deeper in the inside the projects and getting new knowledge. So hope to meet each other and enjoy your lunch break.